Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, where I've been doing my feature for the last couple weeks on the Math Lovers book, Volume 1. I'm not going to go through what this is, other than to say it's a three-volume series I wrote from 2019 to 2022, and it's available both in paperback and in Kindle on Amazon.com. You can find it either by searching for my name, David Tare, or the name of the book, The Math Lovers Book, and I think you'll enjoy it. But meanwhile, I'm running a series of videos on it, at least on the first two volumes, which are the first two texts. And I'm just right now I'm on chapter 2 of the first volume, so I'm still pretty early in the series. But today I'm going to talk about an important method for computing primes up to a given bound, known as the Sieve of Eratosthenes. And anyway, let's begin. So, what is the Sieve of Eratosthenes? Well, Eratosthenes was an ancient Greek mathematician. He lived in the 3rd century BC. He did two really amazing things, I think, for his time, or for any time, but especially for his time. One thing he did, which is not the Sieve of Eratosthenes, was he made the first accurate measurement of the size of the Earth. Not only did he know that the Earth was round, and I think he's the first person I know who actually knew this way before Columbus, almost 2,000 years before Columbus. But not only did he know it was round, but he was actually able to measure it very accurately. The way he did that was he measured the angle of the sun as its zenith on the summer solstice in two different locations. He made one measurement in Alexandria and another one about 500 miles further north in Cayenne. And based on the difference of the angle of the sun as its zenith, he was able to calculate estimate the circumference of the Earth to within about 2%. I just thought I'd mention that. And Columbus got it wrong by about 80%, almost 2,000 years later, go figure. But anyway, the other thing he did was he came up with this method for computing primes, and it's still, even today, I believe this is still the fastest method known for computing all the primes up to a given prime. It's not the fastest method for determining whether a given number is prime, but it is the fastest method we know to find all the primes up to a given bound. But anyway, it's called the Sieve of Eratosthenes. So I want to describe this method. That's what this video is about. So what do we do? Well, let's give an example. N equals 100. This is the one you usually see in most texts. So let's suppose we want to find all the primes up to 100. So what do we do? Well, we know that 1 isn't prime because 1 is what we call a unit. So, I think in the old days some people did consider 1 a prime, but it really, for the sake of math, it's much simpler not to regard 1 as a prime. Just take my word for that right now. I think once you study primes a little bit more, you'll understand why. But anyway, so we cross out 1, we put it in red, and then we look for the first number in black, and that's 2. And the other thing we have to actually take this for granted that 2 is a prime. It's pretty easy to see that 2 is a prime. I mean, a prime by definition is a number with just two factors, namely 1 in itself. And since 2 is there's only two positive integers up to 2, namely 1 and 2. They both are factors, so 2 is prime, clearly. Pretty obvious. So then what we do, once we've labeled 2 as a prime, we put it in green. So the numbers in green are going to be the primes. And then since we know that 2 is a prime, that means that every multiple of 2 that's greater than 2, namely every even number greater than 2, 4, 6, 8, 10, 12, so on, those are all composite. Because in general, any multiple of any prime p, kp in other words, when k is a positive integer greater than or equal to 2, those are composite because they have two non-trivial factors, namely p, the prime itself, and every multiple jp, if you like, where j is less than or equal to k, so 2p, 3p, 4p, so on. Those numbers are all composite. So it's pretty clear that every multiple of 2 greater than 2 is composite. So we cross them out. We put them in red. Keep in mind that all the numbers in red we know are not prime. 1 is the unit, and all these other multiples of 2 are composites, so they're not prime either. So then when we're done with that, we look to see what's the first number we didn't cross out, and that's 3, and we know that that one's prime because we didn't cross it out. It's greater than 2, and you can check for yourself that the only factors of 3 are 1 and itself, 1 and 3. So now we know that 3 is prime, so we put 3 in green. And since 3 is prime, that means that every multiple of 3 that we didn't already hit is also composite, like every multiple of 2 was. And of course, we already eliminated some of these, namely the even ones. We already eliminated 6, 12, 18, 24, so on, because those are all even. But what we didn't eliminate were the odd multiples of 3, namely 9, 15, 21, 27, and so on. So we cross those out. And then once we've done that, then the black numbers are the remaining numbers. So all the green numbers are all the primes we found so far, namely 2 and 3. And then all the composites we found are the red ones, except for 1, which is a unit. And then all the black ones we don't know yet. But now we do the same thing we did before. We look for the first black number, and that one's 5. So now we know that 5 is prime. So we put 5 in green. And now, since we know 5 is prime, we cross out every multiple of 5 that we didn't already hit. Well, that's pretty easy to do on this slide because the multiples of 5 are the numbers in the 5th column. There's 10 columns here. Also, the multiples of 10 are, but we don't care about those because we already eliminated them. Those are all even. But the odd multiples of 5 are all the numbers in the 5th column. And so we make all of them red because we know they're all composite. So we've eliminated those. And then again, now we look for the first number on our list that hasn't been crossed out, and that's 7. That's the first black number on this list. So now we put 7 in green, and we cross out all the multiples of 7 that we didn't already hit, namely 21, 35. I think we already eliminated those, actually. There's one other thing I think I should mention here. At each stage, once we find that number p that's prime, we know that we've already eliminated every prime up to p squared, not including p squared. And why is that? Because if you think about the multiples of 7, like 7 times 2, 7 times 3, 7 times 4, so on, we know we've already eliminated those because each of those numbers has a prime factor that's less than 7. 7 times 2 has the prime factor 2. We already crossed that one out. 7 times 3 has a prime factor 3. We already crossed that one out. 7 times 4, since 4 is a multiple of 2, we crossed that one out. 7 times 5 we crossed out because we already eliminated every multiple of 5. 7 times 6 because 6 is a multiple of 2. Again, that's an even number. So you can see that 7 times 7 was the first number that we didn't eliminate. So we have to eliminate that one. And I think the only other numbers we didn't eliminate are 77. So 49 we have to eliminate. Also 7 times 11, which is 77, and 7 times 13, which is 91. So we eliminate those 3 numbers when we get to 7, and 7 itself. Well, 7 was prime, so we put it in green. And now we're done. And why are we done? Because the next number on our list that we didn't cross out is 11. But 11 is already greater than the square root of 100. The square root of 100 is 10. And just like I said for 7, once we eliminate 11, once we put that one in green, then we know that we don't have to eliminate anything else because the first number that we'd have to eliminate would be 121. 11 squared, that's already bigger than 100. So we've eliminated all the numbers that aren't prime. They're all in red. And all the remaining numbers are either green or black. And it's, like I just said, since we know that every number we didn't eliminate is prime, we can just read off the other primes. They're all the remaining numbers in black. And it turns out there's exactly 25 primes that are less than or equal to 100. And they're all the green ones and the black ones. I might as well read them off for you. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. Actually, I did that from memory because I memorized all the primes up to 100. They're not all that hard to memorize, just 25 numbers. Anyway, those are all the primes up to 100. And there was nothing magical about 100. We could have done this up to 1,000 or a million. Of course, it would have taken a lot longer. But it's easy to write a computer program to do this. And this is actually how you can compute lists of primes up to some big, huge, bound. You could easily write a computer program to apply the Sieve of Eratosthenes and find them all. I'm just going to tell you one more story before I get off. I actually got in trouble for this about 40 years ago. I remember when I was living in Chicago and I was doing my research in physics, and at one point they gave me access to this Cray supercomputer, which I think was one of the fastest computers in the world at that time. This is the late 80s, around 86, 87. I don't remember the exact year. But they wanted me to, work on my thesis project, which was on I think it was what was it? QCD. Yeah, it was. I was working on the I'm not gonna lattice gauge theory, which is a very complicated area of quantum chromodynamics, high energy physics, and they gave me access to the Cray because they thought it would help me with the calculations I had to do on on the I think yeah lattice gauge theory. I didn't really know what I was doing with lattice gauge theory, by the way. I ended up dropping out of physics. I didn't really understand what I was doing too well. But the reason I got in trouble was because instead of using the Cray supercomputer, which is a very expensive computer you have to rent time on it. And the research group I was working for, was paying for my time to program to write code for the Cray supercomputer. But instead of using it to do the QCD calculations, which I didn't know how to do anyway, I decided to calculate all the primes up to a million. I actually wrote code for the Cray supercomputer to apply the Sieve of Eratosthenes, compute every prime up to a million. I don't know how much computing power that took for the Cray, but I think it was pretty expensive. I don't know how much it cost, but I think I do remember getting in trouble for doing that. Uh, they didn't want me spending research money on computing primes, which was already known. But I thought it was pretty cool. I ended up with a list of all the primes up to a million, of which there's about 100,000. So anyway, I just thought I'd share that story with you guys. It happened almost 40 years ago, so I don't think I can get any more trouble for it now, even for telling you guys about it. So I'm no angel. I've done some kind of mischievous stuff in my day. But anyway, that completes my lesson for today on the Sieve of Eratosthenes. Thank you for watching. Long live math, and I'll see you guys next time. Bye.